start. Okay, now, chapter 10 deals with Jordan canonical form. As you know, if a matrix is diagonalizable, everything is much easier. But most of matrices are not diagonalizable. Okay? The Jordan canonical form or Jordan normal form is an upper triangular matrix of a particular form called the Jordan matrix. A simple block diagonal matrix or Jordan block, representing an operator with respect to some basis. Okay, any square matrix has a Jordan normal form or Jordan canonical form if the field of coefficients is extended to one containing all the eigenvalues of the matrix. Okay. Since each matrix has a corresponding Jordan canonical form which is similar to it, all computations can be done with this simple upper triangular matrix. In this chapter, we will study how to find the Jordan matrix which is similar to any given matrix and how to find generalized eigenvectors. In section 10.1, we will introduce a dot diagram to find the Jordan canonical form of a given matrix. If a given matrix is diagonalizable, then it's okay. It's easy. However, not every matrix is diagonalizable. So in this section, we introduce a method for finding a Jordan canonical form of a non-diagonalizable matrix by a similarity transformation. Okay. Okay. Let's review concept of matrix diagonalization. For example, if we matrix a diagonal matrix like this and a 3 by 3 matrix like this, which is not diagonalizable. This is diagonal matrix, so it's diagonalizable. This is non-diagonalizable. If it's a diagonalizable matrix, then we can easily find D and P that makes A is equal to P inverse DP. Particularly if it's a unitary diagonalizable, this P inverse can be easily found by just P conjugate transpose. If it's a real matrix, then P star is same as P transpose. So we can have orthogonally diagonalizable. But for the non-diagonalizable case like this, then we have, by Schur's theorem, we can find the upper triangular matrix T and the unitary matrix P that makes A is equal to P star TP. Okay, but the Jordan canonical form is this way. We are looking for the invertible matrix P that makes P inverse JP. The A is equal to P inverse JP, where this J has a special form of an upper triangular matrix whose super diagonal entries are only 1 and 0, and all other entries except the main diagonals are 0. This is a very special form, easy form. So for every square matrix A, not necessarily diagonalizable, one can obtain a block diagonal matrix called the Jordan canonical form matrix, which is similar to the given matrix A. Okay. This is a review of a diagonalization of a square matrix. If A is an n by n matrix, and then A is diagonalizable if and only if it has n linearly independent eigenvectors. But you know, not every matrix is diagonalizable. A normal matrix is unitary diagonalizable, always. But you know, not all diagonalizable matrices are normal. Okay? If a matrix is diagonalizable, then each eigenvalue of A generates an eigenspace with a dimension equal to the algebraic multiplicity of that eigenvalue. So algebraic multiplicity and geometric multiplicity are same for all eigenvalues. if a matrix A is diagonalizable. Okay, this is what you already know. Here is the first theorem. Let A be an n by n matrix with T linearly independent eigenvectors. Then A is always similar to a matrix JA, where U star AU is equal to JA for some unitary matrix U. Furthermore, we have this JK has this form. The eigenvalues on the main diagonal and ones on the super diagonal, and all other entries are 0. So it's a very simple upper triangular matrix. There's no other coefficient. We have this matrix only has eigenvalues and zeros and ones. That's it. An upper triangular matrix. Important thing is the size of this all submatrices. Some of the size of these submatrices are the size of the original matrix A, which is n. Okay, we call this is a Jordan block. JK is called the Jordan block, corresponding to an eigenvalue lambda I of A. The block diagonal matrix JA is called the Jordan canonical form. So this is called the Jordan canonical form of A, and this is one of the Jordan block in that canonical form. The Jordan canonical form of a matrix A is a block diagonal matrix composed of Jordan blocks, each with eigenvalues of A on its respective diagonals. Ones on its super diagonal and zeros elsewhere. Okay? Like this. Remark. What's the property of Jordan blocks? For a given eigenvalue lambda I of an n by n matrix A, its geometric multiplicity is the number of linearly independent eigenvectors associated with lambda I. Hence, it is the number of Jordan blocks corresponding to lambda I, and the sum of sizes of all Jordan blocks corresponding to an eigenvalue lambda I is algebraic multiplicity. So, eigenvalues are on the main diagonals, and those are the of J, Jordan canonical form. If the geometric multiplicity and algebraic multiplicity of every eigenvalues of A are equal, then the size of every Jordan blocks is one by one, and sum of the algebraic multiplicity is same as sum of the geometric multiplicity, which is the size of A. So the matrix has all one by one submatrices on the main diagonals. All the Jordan blocks are one by one matrix. So it is a diagonalizable matrix. So this is the condition to be a diagonalizable matrix that you already know. We call this type of matrix is a simple matrix. Okay? If it's diagonalizable matrix, then we may call it as a simple matrix. Let's see an example of JA. This is one example of a Jordan canonical form. The characteristic polynomial of this JA is what? This. So characteristic polynomial of a given matrix A is same as this. The characteristic polynomial of similar matrix is same as the characteristic polynomial of the original matrix. So the characteristic polynomial of the original matrix can be written in this way. As you see, 2, 4 here. How many 3? Eigenvalue 3, there are 2. And there are 0 eigenvalues of 2. So 4, 2, 2. This is an 8 by 8 matrix. So this is a Jordan form of some 8 by 8 square matrix A, who has 3 distinct eigenvalues with the multiplicity 4, 2, and 2. Okay, here, notice how the algebraic multiplicity of each eigenvalues determine the number of times that eigenvalue appears along principal diagonal of JA. 2 appears 4 times, while 3 and 0 appears 2 times. Okay? And hence the algebraic multiplicity of 2 is 4. Okay. You can easily verify the sum of the size of all Jordan blocks corresponding to a single eigenvalue is also equal to its algebraic multiplicity. Okay. Here, the important thing is the geometric multiplicity. The number of Jordan blocks corresponding to that eigenvalue is same as the geometric multiplicity of each eigenvalues. So, geometric multiplicity of 2 is what? So, what is the number of Jordan blocks corresponding to the eigenvalue 2? How many? How many Jordan blocks that we have for eigenvalue 2. 2 blocks. Okay? Which means we have 2 linearly independent eigenvectors. So geometric multiplicity of eigenvalue 2 is 2. But what about this? For 3, we have 1 Jordan block. That means 3 has 1 linear independent eigenvectors. So we have 1 block. Eigenvalue 0, we have only 1 block, 1 Jordan block, which means it has only 1 linear independent eigenvectors. Okay? So geometric multiplicity is 1. So if you can find the geometric multiplicity, then you can say, you now know how many Jordan blocks that you have corresponding to that eigenvalue. Okay? That's what it says, this example says. Here, for a 5 by 5 square matrix A, if A has only 1 eigenvalue lambda with 1 associated linear independent eigenvector, then the Jordan form of A is the following, like this. Okay? This is, so, Jordan block. So, this is a 5 by 5 matrix, has only 1 eigenvalue, so we have the eigenvalues are all on the main diagonal, and it has only 1 linear independent eigenvector. So it has 1 Jordan block. So we have a 1 Jordan block like this. Okay? In this case, what's the geometric multiplicity of eigenvalue 5? Okay. Okay. Yeah. This is the geometric multiplicity of the eigenvalue lambda is 1 and algebraic multiplicity of lambda is 5. Okay, then how to find the Jordan canonical form? I have to show you. We have 5 minutes left here. So I will go briefly the proof and I will introduce the theorem. So for a given matrix A, we can have a Jordan canonical form like this. For the corresponding eigenvalue lambda 1 and lambda 2 and lambda 3. So AIs, each AI corresponds to the Jordan block with the eigenvalues lambda I along its diagonals. So if we can find the A1 and A2 and AK, then we can easily find JA. So now we can concentrate to find the AIs. Okay? So AI has Jordan, AI is a Jordan, the direct sum of a Jordan blocks corresponding to eigenvalue lambda I. So those are the Jordan blocks. And all we need to do is how if we can find the general method finding AI, then we can find the A1, we can find A2, and we can find AK. When A has a K distinct eigenvalues, then we can have a Jordan canonical form. So we can now concentrate on this AI. Knowing this structure, we can easily find the Jordan canonical form JA. Jordan canonical form is uniquely determined up to the order of the blocks. For each eigenvalues lambda I consists of Li Jordan blocks. Let us find the size of each of Jordan blocks in AI. Okay. The number of Jordan blocks in AI, L, and their corresponding size, P1, P2, and PL is determined by calculating the length of A minus lambda I. Without loss of generality, we can write PIs in a decreasing order. And now, for the eigenvalue lambda, the dimension of its corresponding lambda eigenspace is geometric multiplicity. Using L and PT, we introduce a sequence of points to easily calculate AI. This is called the dot diagram. This dot diagram dots in the dot diagram are configured according to the following rules. This is the property. First, dot diagram consists of L columns, and counting from left to right, the jth column consists of kj dot, jth columns kj dot, that corresponds to the eigenvectors of xj, starting with the initial vector at the top and continuing down to the end vector. So this is the typical form of a dot diagram for AI. Here, the x1, x2, and xl are linearly independent eigenvectors associated with the eigenvalue lambda I. And rj denotes the t number. Rj denotes the numbers of the dots in the jth row of the dot diagram. Like this, the numbers. You delete this t. We denote the number of dots in the J's law of the diagram. So the R1 has this many, R2 has this many, so R like this. Okay, with this. So now I will let you know how to find these dot diagrams. Consider the following example. For 9 by 9 matrix AI, the number of Jordan blocks containing AI is L. The size of the Jordan blocks is completely determined by these PIs. To see this, we have L is equal to 4, so we have 4 Jordan blocks. P1 is 3 by 3, and P2 is 3 by 3. So P3 is 2 by 2, P4 is 1 by 1. In this case, it is uniquely determined as 4 blocks. And 3 point means there are 3 blocks bigger than 2 by 2. There are 2 blocks with of size Jordan block whose size is bigger than 3 by 3. So we have 2 big 3 by 3 matrices, and we have 3 Jordan blocks bigger than 2 by 2, and we have 4 Jordan blocks bigger than 1 by 1. So from this, what we can see is if we subtract this gives us the number of 1 by 1 Jordan block and number of 2 by 2 Jordan block, number of 3 by 3 Jordan blocks, isn't it? So this gives this theorem. For for M by M matrix, Rj denotes the number of dots in the J's law of the dot diagram of lambda I, then the following are true. R1 is equal to n minus rank of A minus lambda 1 I, lambda I. 2. If J is bigger than 1, then Rj is the difference between this length and this length. Here, J and J minus 1 here. So this is always bigger than this, bigger than or equal to this. So find R1 and then R2, R3, and R4 until it is non-negative. Then addition of these Ri's are same as n minus rank of this, which is same as the algebraic multiplicity of lambda I as an eigenvalue of A. Then R1 is this, R2 is this minus this, which gives us this. So this we have the theorem. The number of dots in each row Rj means the number of blocks of size at least J by J. So from the theorem, let's see these 3 examples, three examples. Here, from here, these 3, the matrix A for this one, find the characteristic polynomial. Then we have eigenvalues. For here, the algebraic multiplicity of 2 is 3 now, and this is a characteristic polynomial, have 2 distinct eigenvalues. For lambda is equal to 3, this is a singleton eigenvalue. If algebraic multiplicity 1, we have only 1 dot. For this, we have 3 dots. How it is located? Find R1, which is 2, so point out 2 points. R2 is 1, so point out 1. We have 3 points. So now we have 4 points for 4 by 4 matrix. So what this means is we have 1 by 1 block. We have 1 by 1 block of 2. Of 3, and we have how many? We have R1 is equal to 2, R2 is equal to 1. This means we have 1 2 by 2 matrix and 2 Jordan blocks of size bigger than 1 by 1, which means this. We have 1 2 by 2, so what's left from 3? So we have only 1 left, 1 by 1, like this. For here 3, and we have 2 Jordan blocks. Yes, one should be 2 by 1. 2 by 2 and the others will be 1 by 1. This can be done by to find the Jordan canonical. If you do find the Jordan canonical form of A, then this command gives you the exact same answers like this, isn't it? Same Jordan blocks. Find the Jordan canonical form of A like this, then use if you can find this characteristic polynomial like this, then you have what? 2 eigenvalue 2 and 4 with algebraic multiplicity each 2. Find the dot diagrams 1 and 1 here, like this. This means you have 1 Jordan block. That's it. You have 1 Jordan block. You don't have to worry. Here you have 2 Jordan blocks for this, which means you have 1 Jordan block for 4 and 2 Jordan block for eigenvalue 2. You can do the same thing, giving the sage command on finding Jordan canonical form of A, which gives you the same Jordan canonical form. Okay, I have given you informations here. Okay, this has the full details of Jordan canonical form. I think you can go through it, check it. If you understand the theorem, then you'll be able to find the dot diagram. Also, those same thing can be done by giving the command of Sage to find the Jordan canonical form. That's it for section 10.1. Any questions?